Today we are going to look the furnace through a different lens, the lens of metallurgical forensics. Stability in blast furnace is not just about a gas flow, it's about the structural integrity of your body at the 1500 degrees centigrade. So look at the visual on your screen. That 3D wireframe is not just a model, it represents a high-stake environment where raw material meet extreme kinetics. So by the end of this session, you are going to walk away with three critical deliverables. What are those? So first, the ability to identify the permeability cliff edge before burden doesn't halt. Second is a deep understanding of why alkali vapors are a silent killer of your coke matrix. And finally, a data-backed strategy to justify the premium raw material cost against the staggering price of emergency shutdown. So we are not just operating a reactor, we are protecting a multi-million dollar asset. And to understand how to protect this asset or the furnace, we first have to quantify the massive financial blind spot currently draining our profitability. So coming to our next slide, which is about the big picture. So now look at the telemetry on the right side of the screen. Our expected model shown in electric blue suggests a 24-month to year lifespan. But the actual ground truth, highlighted in that neon coral warning, is less than 6 months. So that's a 75% variance that most operators are just living with. So we have been blaming a thermal fatigue, but the forensic data proves we are actually dissolving our own infrastructure from inside out. So note the slip frequency metric. We are seeing over 8 per week, a 300% increase over baseline. Every time that burden sleep, uh, you are looking at a erratic chemistry, thermal instability. So the bottom lines are three emergency stops per quarter are costing us $3.6 million in lost productivity and hardware also. We think we are saving on fuel, but we are actually vaporizing our components. We have to stop looking at symptom and start analyzing the data landscape of the failure itself. This transition from symptomatic troubleshooting to forensic analysis require a sophisticated data architecture that bridges the gap between sensors and the lab. And in this context, we are coming to the data landscape, that is the forensic architecture. On this slide, you will see our forensic architecture. Notice the node map on the left where we have interconnected live sensor telemetry. The blue ops with the post-mortem microscopy, the glowing green echoes. So we are not just looking at one data point. The table below details our sources a high resolution thermocouple array providing 14 million row of time series data coupled with nanometer scale ACM and EDX analysis of failed tuyeres. This is where the magic happens. By overlaying thermodynamic sensor drift with a microscopic analysis, we have linked the macro level gas channeling directly to micro level carbon solution loss. In simpler terms, when our top gas analysis shows a shift in carbon monoxide and carbon dioxide or a ratio of it, it's a direct signal that your coke is being eaten alive at the grain boundary. So if you ignore the nanometer, you will never master the megaton. We need to focus on the first measure inside this data revealed regarding the coke strength. That microscopic degradation leads us directly to most dangerous threshold in iron making, the permeability cliff. And in this slide of the top inside, you can say top inside one, the permeability cliff. Now look at the radiant curve on the left. This is the permeability cliff edge. We have plotted slips per day against Coker's strength after reaction or CSR. Follow the blue line from 62% CSR down to 58%. It looks like a gentle slope, right? But look what happens the moment you hit 58%, the critical threshold. The line turns into neon coral arrow pointing slight, not a massive straight down. At 57% CSR slip, a skyrocket to 8 per day, massive 344% collapse in stability. So physically what's happening is the internal void fraction are vanishing. Fines are choking the cohesive zone, pressure spikes and the body descent halt instantly. Here is simple consequences. If your procurement team buys coke at 57% to save $5 a ton, they are effectively choosing to halt the furnace. Stability is a binary state, and 58% is the border you cannot cross. But what causes seemingly strong coke to suddenly lose its structural integrity? The answer lies in a chemical paradox. And our next slide, which is about the top insight too, that is about a alkali paradox. So this is what I call the alkali paradox. So look at the split screen macro photography. On the left, the healthy coke matrix shows a robust emerald green cellular structure. On the right, the alkali affected matrix is riddled with the magnet of micro fissures. So this is the trick, that is alkali rich coke actually appears robust at ambient temperature, but as it descends and hit that 1000-degree mark, the potassium interaction forcefully expand the graphite lattice. It creates a false skeleton that shatters the moment it takes a high temperature load. So look at the data table. At ambient strength, the alkali coke is nearly identical to baseline at 84%. But look at the hot strength or the CSR. The baseline stays at 65%, while the alkali affected coke create to 42%, a 35% drop. So operationally, this means your strong coke becomes dust exactly where you need it to be a spacer. So suffocating your furnace breathing is quite obvious. So while alkali destroy the structure, impurities like ash create a compounding thermal penalty that further suffocate the hearth. So now coming to our top insight number 3, the ash penalty multiplier. Now let's talk about the ash penalty multiplier. This is the bar on the left represent your fuel efficiency. See that teeny coral block, that's a microscopic ash impurity. It looks insignificant, but look at the table. A move from 11% to 13% ash content, just a 2% swing requires an additional 45 kilogram of slag per ton of hot metal to flux out. So that extra slag is not just weight, it is a thermal sponge. It devours their energy, raising the slag viscosity and literally suffocating the hearth. So we see 3.2% jump in the fuel rate just to keep the furnace from chilling. This is the definition of penny wise and pound foolish. By trying to run cheap high ash fuel, you are inflating your slag volume and destroying your thermal reserves. So we need to look deeper into how this degradation actually progresses through the material. To stop this thermal drain, we have to understand the specific mechanism of how coke fails using the PSVP framework. So coming to our next slide about a deep dive one, that is PSVP framework and degradation. We use the PSVP framework, that is process structure, property and performance. So look at this glowing cross-sectional schematic of a coke particle. The outer surface shown in a blue looks stable, but look at the core, that's where the severe pitting and failure occurs. Damage start at the grain boundaries, not the surface. If you look at the data table, where the first millimeter of the surface, you only have 12% carbon solution loss. But as you go deeper, 3 to 5 millimeters in you hit 88% loss. This is the core failure. Processing creates a fissure that allows CO2 gas to penetrate deep into the particle, and this gasification destroys the mechanical performance right in the heart of cohesive zone. So when the core vanishes, the particle collapses into the fines. This is not just chemistry, it's a structural engineering at a molecular level. So if the structure fails, the entire furnace performance follows. While coke failure happens in Bachane, our cooling equipment faces its own silent, irreversible thermal path to destruction. So now in next slide, which are coming to deep dive to the thermal pre-shock vector. So let's move to the cooling system and the thermal pre-shock vector. On the left you see before laminar flow and optimal cooling in the copper stave. On the right the after show 3 millimeters of calcium scale buildup. That scale acts as an insulator, creating a vapor lock. Follow the red line on the graph. Notice the spike in the stave water temperature 14 days before the actual failure. We call this the thermal pre-shock. Merely 3 millimeters of a scale reduces heat transfer efficiency by 40%, initiating an irreversible thermal runaway. By the time you hit T minus 0 days, the copper matrix reaches 1083 degrees and melts. The so what factor here is your lead time. You have a 14-day window where the data is screaming at you that a burnout is coming. So if you are not monitoring the delta T and heat flux, you are just waiting for the explosion. So when that explosion happens, when the tear finally melts, we have to perform a hearth autopsy to find the real culprit. And this slide, which is about a root cause analysis of the details of the hearth autopsy. So when a tear fails, most people point at the cooling water, but look at this hearth autopsy fishbone diagram. The descent from the blue, the symptom into neon coral, the root cause. Why did the tear melt? Because the slag dripped onto the copper. Why did the slag drip? Because of extreme peripheral gas channeling. And finally, why did the gas channel? Because the high reactivity coke degraded into fines, blocking the center and forcing the gas to wall. So the root cause is high reactivity coke, not a cooling system failure. The cooling failure is just the final symptom of the metallurgical breakdown that started days earlier. We have to stop fixing the symptom and start controlling the chemistry of our input. If we don't keep the gas in the center, we will keep burning copper no matter how much water we pump through it. So this balance of gas and solid is governed by the law of aerodynamics, which we can map onto a state diagram. So coming to the state diagram, uh, which is about the aerodynamic safe zone. And to keep the furnace stable, you must stay in the emerald zone of this aerodynamic state diagram. On the left, we have a breeze respecting and representing our burden supported by gas flow. In the emerald zone, where the void fraction is above 45% and gas velocity is under 120 meters per second, you have a smooth descent. But look what happens in the coral zone when the void fraction drop below 40%, the gas velocity exceed 140, the breeze breaks. This trigger immediately fluidization and violent slipping. This is not a suggestion, it's a physics. High gas velocity combined with a low void fraction caused by those coke fines we talked about will lead to a slip every single time. Your job as an engineer is to maintain these strict thermodynamic boundaries. If you feel the furnace tighten up, you are already moving into yellow hanging residue. So this tightening of the furnace is often caused by scaffolding, which as we will see is violently coupled with our alkali input. So coming to our next slide, which is about a correlation matrix, the web destruction. So this correlation matrix shows the web of destruction inside the stack. So look at the thick glowing orange arc between alkali input and the scaffold growth. The correlation coefficient is 0.92. In the world of statistics, that an extreme coupling, this proves that scaffolding is not random. Alkali condensation acts as a primary chemical adhesive, binding fine ore and coke directly to your refractory wall. Notice the weaker correlation of 0.12 for the blast temperature and slip frequency. This tells us that you cannot just hit your way out of a scaffolding problem. If you have high alkali input, you will get a scaffold. So those scaffold restrict the furnace diameter, increasing the gas velocity and lead us right back to the violent slips we saw on the previous slide. So everything is connected. To solve this slip, you have to solve the scaffold. To solve the scaffold, you have to restrict the alkali. So by understanding these correlations, we move from reactive firefighting to true predictive modeling of the furnace future. So now coming to the predictive modeling, the horizon line. So we can now see the future. This is the horizon line predictive model. By mapping two gas CO-CO2 ratio anomalies against silicon temperature lag in the hot metal, we can forecast a chilled hearth 48 hours before it freezes. At T minus 48 hours, we see a 0.15 shift in the gas ratio. The hot metal silicon might still look normal, but our algorithm already flags a 65% probability of a hang. By T minus 24 hours, that probability jumps to 89% as silicon start dropping. If you wait until T minus 2 hours, when the gas is erratic and silicon is below 0.4%, failure is 99% imminent. So the operational impact here is the power of preemption. So 48 hours is enough time to adjust the burden and prevent the catastrophe. So if you wait for the symptom to show up in the iron, it's already too late. But if the worst happens and the hearth does chill, we need a modern intervention architecture to bring the furnace back to life. And our next slide, which is on a very right direction about the intervention architecture, that is the oxy-fuel. So when the heart chills, the dead man zone becomes a paralyzed block of pulled coke and slag. Traditional manual lancing only target the periphery and has a dismal 15% success rate, often taking over 72 hours. So look at the oxy-fuel system architecture. We use refractive protected lances to inject extreme localized heat directly into the core of the dead man. We are targeting the paralysis itself. So this technology liquefies the solidified slag matrix in just 18 hours with an 85% success rate. So the factor is massive. So you are saving over 50 hours of downtime. In a large furnace, that's 10 of thousand of tons of lost production. So we are moving from brute force lancing to surgical thermal injection. So this is the ultimate insurance policy, but the goal remains to never need it by managing our cost and quality upfront. So this brings us to a utilize ultimate questions. How do we balance the cost of this premium material against the risk of those failures? And our next slide, which is about the cost matrix, and the price of irregularity. So let's look at the cost matrix. This 3D isometric chart tells the real story of blast furnace economics. The tall coral bar on the left is the $11.5 million annual cost of clear burnout. Add the 2.1 million for the severe sleeping, and you are looking at $13.6 million in unplanned expenses. Now look at the green bar. That's the $4.5 million cost of switching to premium high CSR coke. So operating blindly with a cheap fuel costs you 13.6 million. Investing in quality costs your 4.5 million tons. That is the 10 times return on the investment. So we have to stop seeing the premium coke as a cost and start seeing it as an offset against the catastrophic loss. So predictive metallurgical control is not just an engineering preference, it's a financial imperative for the survival of the plant. So to capture the ROI, we must institutionalize these findings into a strict non-negotiable baseline strategy. The baseline, what is that baseline strategy? And the baseline is a strategy about the metallurgical mandate. And uh, in this slide, we conclude with the metallurgical mandate. This is not just a guideline, it's a radar for your operation. So look at the targets in the data table. We are moving from a current state of 57% CSR to a mandated target of over 65%. We are slashing our alkali limit from 3.5 down to below 2.0 kilogram per ton of hot metal, and we are strictly enforcing a voidage buffer of at least 45%. So as engineers, we do not just operate the furnace, we protect this architecture. By enforcing these physical limits, we eliminate the blind spot, kill the alkali paradox, and stay firmly in the aerodynamic safe zone. This is how we can run our world-class operation of the furnaces.